Fantastic. Tom Christiansen,
All right.
grounding in mixed signal circuits, or why star grounding sucks.
Take it.
Thank you, Tom.
Well, thank you, Jim. That was quite the introduction.
And you're off at noon, just FYI, top of the hour.
Does the roof cave in or? Okay. Okay. All right. So I'm Tom Christiansen. I run Neurochrome, where I make circuits for DIYers and also a little bit of business to business and do some consulting on the side as well. And I recently designed a DAC for a client. This is actually prototype number 2. Prototype number 1 provided remarkably poor performance. And it was just one of those head scratchers, at least at first. Because I had done everything right, or so I thought, and I had kept the analog ground separate from the digital ground and joined them at the power supply, audiophile nirvana, this should just work perfectly. And I get it back and I build it up, and in the meantime, I had read up on grounding in mixed signal circuits, and as soon as I plugged it in, I'm like, oh. And then the palm met the forehead, and I realized I had a really good talk for burning amp. So this is the story of the little amp that couldn't, or the little DAC that couldn't. And now my remote has stopped. Oh, I see. So what is star grounding? Star grounding is basically when you take all the grounds in the circuit and you run it to a central point. So in this case, it would be this, looks like a chassis stud that would mount there. And that is touted as sort of the holy grail of audiophile nirvana, where it solves hum loops and ground loops and everything, but it also creates a bunch of inductance in series with all the ground nodes. On top of that, you can actually get coupling between these signals that flow in parallel here. So now your grounds start talking to each other. So let's have a look at what that would imply. So let's say we have a simple circuit here. We have a couple of buffers, and they each have a ground reference that's connected here, but connected with this shared trace where we have a ground in the middle, so basically a star ground. And let's see what happens if you start running a current through this ground net. So just to get some numbers on it and make it a little more practical, let's say there's an inch of board trace, so about 25 millimeters. And we can estimate that the impedance, or excuse me, the inductance of a PCB trace is roughly a nanohenry per millimeter or 25 nanohenries per inch. And you can calculate the equivalent resistance just from the sheet resistance of the copper. And that's, I think, 0.5 milliohms per square, something like that. So it works out like this, but let's compare that to, let's say we put it on a ground plane. So with the ground plane, I mean, it's no surprise we get much lower resistance. But it might be a bit of a surprise that we also get much lower inductance. And let's see what difference that makes when we run an amp of current through this ground net. So basically, the red trace here shows the air voltage that develops between the two grounds as function of frequency for star ground. And the green trace here shows the air voltage that develops if you do the same with the ground plane. And note that the y-axis is logarithmic, so there's actually a factor of 100 almost difference between these two. So with a ground plane, you get a much, much lower air voltage. And that's sort of the main problem. Another problem is that all this inductance is really good at acting like an antenna. And if you have a smaller inductance, you have a smaller antenna. And that means that you're much less susceptible to stuff being radiated into the circuit, but you're also much less likely to radiate out into the world. So minimizing inductance is a good thing. So let's have a look at, well, what exactly is inductance? And specifically in this case, self-inductance. And you might have seen this experiment done in physics class back in, I don't know, 7th grade or something like that. I'm assuming some of you are young enough to remember back that far. So you take a horseshoe magnet usually, that works nice for a demonstration. You run a wire through it, and then you run a current through the wire. And as you may remember from then, is if you grab the wire with your right hand and with the thumb in the current flow direction, then the magnetic field flows around the wire like so. And that means that when you run a current through the wire, there's a force between the magnetic field of the stationary magnet that interacts, and the wire starts swaying out of the into or out of that horseshoe magnet. And that's cool. And we can do some math here, and we can define the inductance as the magnetic flux divided by the current. And from that, we can also figure out that if we have a certain amount of flux, a certain inductance, then we get a certain amount of current when they interact on each other, or when the flux interacts on the wire. And that also means that if we have two parallel conductors and we run a current through the first one, so this one here, then that will set up a magnetic field around itself. And some of that magnetic field will spill over to wire number 2. And when it does that, it induces a current in wire number 2. And we can model that with basically two coupled inductors, where the coupling ratio is the mutual inductance between those two wires. Okay, so now we have a situation where wire 2 is just sitting there. So this wire here is just sitting there minding its own business, and wire 1 has a current flowing in it. And now wire 2 has this air voltage developing in series with it, basically. And we can calculate that air voltage just from Ohm's law, as the impedance times the current is equal to the voltage. And that's what we have here. Just remember that omega, in this case, so this lowercase omega, is just mathematical shorthand for 2 pi times the frequency. It's the radian frequency, so in radians per second instead of cycles per second. That's the only difference. When you read omega, just think frequency. So we can also model this as a pair of circuits coupled with a transformer with a coupling ratio that's basically set by the mutual inductance. So how do we minimize this coupling? How do we minimize this air voltage? So just a quick note, I use the terminology that Henry Ott is using because I took a lot of his figures from his book, Electromagnetic Compatibility Engineering. So that he uses the term noise voltage. I would rather use air voltage. But anyway, it's the same topic or the same thing we're talking about. So basically what we have here is we can use Faraday's law to figure out how much voltage do we actually get developed if we have a certain amount of magnetic flux interacting on this wire loop. And that is the equation shown here, where we have a frequency term, and then we have B is the magnetic flux, A is the area of the loop, and cosine theta is cosine to the angle of attack of this magnetic field on the loop. So for example, I mean, if we want to minimize that air voltage, the 4 knobs we can turn is basically, well, we can reduce the W or the J omega term, reduce the operating frequency. That might not be an option in a lot of cases. We can reduce B, so we can reduce the magnetic coupling, or the flux density rather, and we can do that by moving things further apart. That might also not always be an option. We can also change the angle to 90 degrees. And can any of you see why 90 degrees is the magic number? Well, cosine. Cosine 90 degrees is what? 0. Ta-da. And that's, some of you might have played around with a tube amp where you rotated the power transformer 90 degrees to the output transformer. That's exactly what happens. What you probably also observed is that when you do that, you don't get perfect cancellation. And that's because the magnetic field doesn't flow out in nice parallel lines. It sort of flows out like that. So, and you might get perfect cancellation on, that one magnetic field line right in the middle, but everybody else, you don't get perfect cancellation. So it works okay, but not great. The biggest bang for your buck, and what I'll be spending most of my time here today talking about, is reducing the loop area. And that, I mean, often it's free. In fact, it might actually be a negative cost in the sense that your circuit board becomes smaller. So that is really a good way to approach this. And if you take anything away from this talk today, take that away from it. Minimize your loop areas. So let's look at examples of that. So we have a simple circuit here, 2 resistors in parallel. This should not be earth-shaking. And this is what the layout could look like, where we have resistor 1, resistor 2, and then some traces connecting them. But we immediately see that we have this enormous loop area. that they encompass. So what we could do to fix that is to move them closer together. So now our area looks like this and much smaller. What we could also do is, what if we change them to surface mounted resistors? So in this case, I'm comparing 2 quarter-watt types. So these are 6.3 by 2.5 millimeters in diameter, standard quarter-watt size with 0402, which is pretty small. But still, you see a dramatic reduction in loop area. And that's actually just the area looking down on the board from the top. What you also need to consider is if you look into the edge of the board, the current will flow up into the resistor and back down into the board, and that has a loop area as well. So with the surface mounted components, simply because they're not as tall, that loop area gets reduced also. So another thing we could play with is, let's see what happens if we have a different component placement. And in that case, we can actually reduce the loop area to something that's about like yay. Unfortunately, we also have this trace in series with the resistors now, and that means that we get an inductance. And I just clicked on, I drew this up in KiCad, and I clicked on the trace, and it'll actually tell you how long it is. So you can use my rule of thumb of a nanohenry per millimeter, or you can actually do the math on it. And this is an approximation. And so that's an approximation for the trace inductance. And it comes out nanohenries per inch if you punch in the height of the trace over the dielectric, or excuse me, over the reference plane, and the width of the trace. And note that this is valid as long as the trace is narrower than the height of the dielectric. So that means basically that as long as the trace is narrower than the height of the board or thickness of the board, then you get a inductance that looks like this, where this is for a super skinny trace, and this is a trace width of 1.6 millimeters on a 1.6 millimeter thick board. So to validate sort of my rule of thumb that I learned in college many years ago, of 1 nanohenry per millimeter, I mean, it turns out that you actually need a trace that's about 2 mils or 0.05 millimeters wide, which is not manufacturable unless you want to pay a lot, and probably still not manufacturable. But it's a pretty good, if anything, conservative rule of thumb sort of guess for if you just want to do some quick math. So now we can use this newfound knowledge to figure out, well, that means we have 17.1 nanohenries in series with these resistors. That's actually quite a bit. In my example from earlier that showed the impact of the air current, I had, I think it was 22 nanohenries. So this is sort of comparable. But anyway, but what about reducing both the loop area and the series inductance? And we can do that by using a ground plane. So now I have drawn the ground plane blue here, and that reduces our loop area to that itty bitty little bit. But it also reduces the inductance between the two resistors. So now we have basically almost a factor of 100 reduction in inductance just by using our copper plane. So that's kind of cool. I mean, you pay for the copper anyway. You might as well use it. Changing gears a little bit. The challenge with ground planes, I think, is that most people don't really have a good sense of where does the current flow in the ground plane. But most of you have probably heard the term, the current flows along the path of lowest resistance, right? I would generalize that and say the current flows along the path of lowest impedance. The difference being that at low frequency, or DC, the resistance is dominating. At high frequency, or RF, the reactance of the inductance is dominating. The big question is then, at what point do we transition from LF to RF, or DC to RF? And thankfully, there was a guy named Kuhne in 2024 who answered that question quite nicely with some nice animations. So he took sort of an elliptical trace, or half elliptical trace, drew that up in an electromagnetic field solver that he had access to, put it on a board that's 2 millimeters thick, so a little bit thicker than normal, with 2-ounce copper. And then he looked at, well, what happens with the current flow as function of frequency? This little trash can looking thing here is just indicating that the source is placed right there. So if current flows out the trace, drops into a via, and then it flows back along the ground plane on the bottom. And at low frequency, that looks like this. And this is not a huge surprise. So this sort of works like one of those thermal images where red is really high current density. So we can see there's a whole bunch of current crowding in the two vias. And then there is sort of a uniform current density in the trace itself. And then the current drops into the ground plane and it sort of creates this sort of blob smear thing. But most of the current actually flows directly from one via to the other. And that's not a shock, right? Because that's the path of lowest resistance. But let's see what happens at RF. This is probably, hopefully not a surprise to most people either. But most people probably don't understand why this happens. But what happens is that the current flows along the trace on the top, drops into the via, drops into the ground plane, and then it flows right under the trace on the bottom of the board. And this is at 100 kilohertz. I mean, it gets even tighter at higher frequency. And why might that be? Well, if you look at the board again, sort of cross-sectionally, you flow out the trace, drop into the ground plane, and flow back. And that forms the lowest amount of loop area. So basically, the current figures out that is where the lowest inductance is, and it follows the path of lowest inductance at RF. So the challenge or the big question is then at what point does the current transition from following the path of lowest resistance to the path of lowest inductance? And that can be figured out by looking at the reactance and the resistance of the structure there. So the resistance is drawn in green here, and you'll see it rises a little bit with frequency. So the x-axis is frequency from basically DC to 25 kilohertz. Yeah. And you can see that the resistance rises a little bit, and that's because of skin effect. Basically, you get some eddy currents flowing in the copper, and that scares the electrons so that they only flow in the surface layer. The blue trace here shows the reactance. So that's the inductive part of this connection. And they cross, to my great surprise, already at 1 kilohertz. So that means that basically frequencies above 1 or at least a couple of kilohertz should be considered RF. I found that really insightful or interesting. And we can also take a look at this simulation here. So now it's basically an animation that runs from DC, or 10 hertz, up to 100 kilohertz. So the first picture, and that's this one, is 10 hertz, and then 1 kilohertz, 2, 3, 4, 5, 6, 7, and so on, up to 10 kilohertz, then 20, 50, and 100. So it's pretty interesting. Already at 1 kilohertz, you start seeing the return current in the ground plane sort of following the trace. And certainly at 2 kilohertz, there's a clear definition of the return current right under the trace. And that's, I mean, I found that surprising. I would have thought that RF was something like a couple of 100 kilohertz at least, but at least with this structure, it starts already at a few kilohertz. So that's kind of interesting. But there might be some of you that's like, a little inductance has never hurt anybody. Well, I took this measurement in 2016, where I took my modulus 86. This would have been a Rev 1.0. And I've just drawn it like a schematic here, but it's an ultra low distortion amplifier. And I played with the series inductance in series with the lower feedback resistor, so the feedback resistor to ground. And I added in the first case 0 nanohenry, so that's just the resistor going straight into the board into a ground plane. The second trace, I don't remember, but I think it was maybe 20 nanohenries, about probably this much worth of wire. And then the last trace, I added about like this much wire, so 2.5 inches, 60 millimeters. And we can clearly see that the THD plus N rises quite dramatically, even starting at around a kilohertz with 60 nanohenries of inductance added. And that's sort of, I mean, if you're aiming for high performance, then, you know, minimizing inductance seems like a good thing. So, yeah.
And at THD plus N, what does the FFT tell us about what's going on there? Is that distortion? Is that noise? What's making that curve rise?
That's a great question. I don't know the answer. I don't remember. I did this in 2016, and I don't think I actually took the FFT. I would think that it is either the signal level that's dropping very slightly, or that all the harmonics simply come up. Because you get a little bit of a reduction in loop gain from that, and that might actually be enough to skew the performance slightly. So if I'm to guess, I don't know for sure, but if I was to guess, I would think that it's the harmonics that are creeping up, especially the harmonics towards the high end. Are there any other questions so far? I'm going a little fast, I think. Okay. So just to summarize here, lower loop area means lower inductance. And that means that you have lower coupling both into the circuit and from the circuit to the outside world. And that means lower noise and lower EMI, so electromagnetic interference. Remember that the current follows the path of least impedance. And that means it follows the path of lowest resistance at DC and the lowest inductance at RF. And RF begins in the audio bank. So let's apply this newfound knowledge to an actual circuit. So now I'm circling back to that DAC that I built earlier. First off, let's talk a little bit, what is mixed signal really? You probably heard the term, but it basically just means that we have both analog and digital in the same circuit or in the same IC, for example. And we usually have a goal of keeping our digital bounce house from corrupting the sensitive analog circuit. So keep the noisy digital currents out of the analog. And one approach that's been touted is to have two separate ground planes, one for analog, one for digital, and then you ground them at a start point. And that all sounds fine and dandy. I think it's a bit misguided though, because we will always have some amount of coupling between the two. If nothing else, there will be some sort of analog chip or analog to digital converter chip, for example, that sits between the two and will have some amount of coupling through that chip. So now we have a huge loop area. And I have a strong suspicion that's actually what wrecked the performance of that DAC I was building. So one approach that has been touted is that, okay, fine, we just scoot the two ground planes closer together. We cut a slot in between them. That's commonly referred to as a moat. And then we have a bridge across this moat that is placed somewhere between, so they only connect at one point, and now life is fine and good. Except we have to, you know, pick the grounding point at some point. What we usually do then is we put the DAC right smack on top of that moat or top of that bridge, and life is good, or so we think. This creates a challenge though, because we need to decide, well, what is analog and what is digital? So what goes on which ground plane? Also, where do we put the bridge? I mean, it was easy in the previous example where we have one DAC. Okay, fine, we put the bridge underneath the DAC, but what if we have two DACs? What do we do in the cases where we need the digital to talk to the analog? So we need to have a wire across the moat. And also, where should this ground connection even be? So let's walk through those with an example here. So this is a CS8416. It's a spotted receiver. It takes like coax or AES3 digital audio in. and it spits out the bit clock and the master clock and the data. And you can see that it has an analog supply and an analog ground and a PLL loop filter, and that's decidedly analog, so that part is easy. And then that must mean the rest is digital. And if we take a look at the pinout of it, we can see that all the analog stuff is basically on the left side, and all the digital stuff is on the right side, except for there's a reset pin, and then there's an address select pin, and those are usually static. So that's pretty good. We can also look at a DAC chip. So this is the AK4493 from AKM, almost known microelectronics. And all the output, the analog output, is on the north side of the chip. And then we have all the digital stuff is on this green power domain. So we can clearly identify the analog, and we can also clearly point out the digital. But then there's the master clock, which for some reason is marked with an AVDD. So is that an analog voltage then? I mean, I can kind of see an argument for making it an analog voltage because you don't want any jitter on the master clock, I'm assuming. But it's so already here, the sort of model of analog on one side, digital on the other side starts to break down a little bit, or we need to at least deal with that. But let's just say we do like this, and we put all the digital stuff together in the middle, and then we have analog going in and analog going out. That means that our board could look something like this. So we have an analog ground plane on the left, we have a digital in the middle, and we have an analog ground plane on the right. And let's just, for argument's sake, place the bridge under the DAC like everybody else does, and connect the analog ground all the way around. Well, that's all fine and good, except this looks an awful lot like an antenna to me. Specifically, once we start accounting for, we'll have some amount of coupling through that SPUDF receiver chip. So now we have a huge loop area on the north side and also a huge loop area on the south side. So now we have a bunch of inductance, we have a bunch of potential for radiation in and out of that area. And a different approach could then be, okay, fine, we put the digital on the south side and we put the analog on the north side. Bridge under the DAC, and then there's some coupling between or through the receiver chip. Okay, so now our loop area at least is smaller, but I still think we can do better than this. The other challenge was, well, what if we have to talk across the moat here? So most can probably visualize the current flow going forward, so coming from the positive supply across this wire here, into this chip here. But then what about the return current? Well, that goes out the ground pin here, drops into this via into the ground plane, and then it has to make it across to this chip, to this ground here. And the only path is this way. So the current flows in this loop here, like I've drawn here. That's another large loop area. So another bunch of inductance, another bunch of EM hassles. So a better way is actually sort of ironically to lengthen the trace, because then the return current looks like this and we have a much lower loop area. I still think we can do better. And there's still an issue. Let's say we have two digital chips that need to talk to each other. This could be the receiver that talks to the DAC through the master clock that's banging away at 33.8868 megahertz. And the way I've drawn it here makes it look like, well, the return current is nice and contained within the digital ground plane. And I don't know if you've ever looked at those cell phone coverage maps that show the cell phone signal ending abruptly right on the state line. And I always get a good chuckle out of those because RF signals don't behave like that. And neither do magnetic fields or electric fields. So this is what the fields will look like. This is looking sort of cross-sectionally into the board. So this is the trace that goes from one chip to the other. This is the reference plane, so the ground plane in this case. And you have the magnetic field and you have the electric field. And let's cut a moat into that reference plane. Now, I realize that I didn't actually change the figure aside from drawing that white rectangle, but the electric field lines will not change very much when you put in that moat. There might be a little bit of distortion because of the discontinuity, but you will have some of the field lines that will terminate on the other side of the moat, which means that your return current, instead of looking like this, looks more like this. Now we're back to big loop area, and also we start having current flow into this sensitive analog circuit. So what can we do about that? Well, one approach that we can take is to make one solid ground plane. So let's look at the case where, well, so one solid ground plane, and then we still decide to partition it. And that means that basically we decide that the analog stuff goes on one side, in this case the north side, and the digital stuff goes on the other side, in this case the south side. But we don't have a moat, we still have solid copper from one board edge to the other. In that case, the return current for an analog chip talking to a digital chip will look like this, where forward current flows through the PCB trace, then it goes through the chip into the ground, and then it flows along the path of lowest inductance to the ground on the analog chip. So this is guaranteed to be the lowest loop area. Similarly, when the two digital chips talk to each other, the return current will follow the path of lowest inductance. You'll still have some amount of electric field that spills over into the sensitive analog circuitry, and the only thing we can do about that is to space them out. The question is, well, how far do we need to space them out? Well, let's take a look at this figure again. So we can look at the current density in this reference plane. So basically, how much current flows per unit area. And I'm just putting this figure here for references to the coordinates that are shown in the next, on the next slide. So basically, W is the width of the trace, H is the height of the trace over the reference plane, and X is the distance from the middle of the trace going perpendicular out into the board. So if you look at the current density in the reference plane, it looks like this. So it's the highest right under the middle of the trace, exactly as we expected. So this is valid for RF. And then it quickly tails off on either side. And if we then look at the area under this curve, we can figure out, well, basically, how far away do we need to move from the trace to have, say, 90% of the current flowing in behind us. And we can get that from this figure. So basically, let's say I just picked arbitrarily 90%. So here, we need to go about 6 dielectric heights away from the center of the trace to get 90% of the current flowing, away from us, basically. And that means we get 20 dB of attenuation just by moving those 7 times H away. So that's what I've drawn here. So what's 7 times H? Well, if you have a 2-layer board, normal standard thickness of 1.6 millimeters, we're talking 11.2 millimeters, or about yay much, half an inch. If you go with a 4-layer board, now typically you have a much thinner dielectric between the top layer and the first inner layer, so layer 1, layer 2. You also have a very thin dielectric between layer 3 and layer 4. And then you have a core in the middle that makes up the difference, so that the total board thickness is 1.6 millimeters. So if you put the reference plane or the ground plane on layer 2, now all of a sudden you only have to move, yeah, exactly 1.4 millimeters away, and that's like this. And then imagine, I mean, for just practical reasons, you probably have to space it out, half an inch anyway. So now suddenly, practically none of the digital return current will flow in your sensitive analog circuit. So spacing is good. The other thing we could do is, well, what if we played with the component placement? And I realized I've cheated a little bit because this pin actually should have been on the top. But let's say this is a microcontroller chip that needs to talk to the DAC for some reason. We could pick a microcontroller pin, an I/O pin that's on the correct side of the microcontroller. And in that case, we get to reduce the loop area quite dramatically. So that's another thing. So now we get both the benefits of the distance here, but we also get the benefit of the much reduced loop area. So that's pretty cool. That basically makes your antenna smaller, they couple less, and they disturb the sensitive analog circuits much less. So now let's go back to the DAC prototype here. And I just put the chipsets I used here, and then also Rev 1 used the star ground. So I had analog and digital ground completely separate, joined back at the power supply. So this is revision 2. And in this revision, these components here, that is basically the digital part of the circuit. Because the pinout of these, of the AK4118 and the AK4493 is actually intelligent enough that if you place them like so, the traces, they only have to go, I mean, I think it's maybe less than a quarter inch, I think. So the rest of the board is on a, I mean, everything on the board is on a shared ground plane. And this is a 4-layer board, so the ground is on layer 2. Let's look at the performance of it. So the red trace here is the performance of Rev 1. That's the one with the star ground. And we're talking almost 10% distortion at full output. That's unsellable. That's just fundamentally broken in my opinion. And with the shared ground, I'm within like a dB of the datasheet performance, which is pretty good. I still think I have room for improvement, and I have some ideas for how to do that. But that is much, much better. And that's just everybody on the same ground. Everybody's happy. Similarly, if we look at distortion versus frequency, with the Rev 1 is markedly worse than Rev 2. And we can also look at jitter. So you can see that Rev 1 has almost 20 dB higher noise in some places. And it's actually so noisy that all the jitter components are completely buried in noise. Whereas version 2 has a nice flat noise floor. There's quite a bit of jitter, and that's because I'm using a coaxial input. I think I can improve on that. If I use the optical input on that DAC, I'm down to just a couple of these jitter components, which is much better. So basically, the DAC that has the shared ground performs much, much better. So basically, to conclude, use a single ground plane, single solid ground plane. Just make sure that you partition your board, so do your component placement such that you have sensitive analog away from digital that's just banging away at some alarming speed. Use spacing to your advantage. And also, keep in mind that, I mean, a lot of these mixed signal chips, they will have, say, one ground pin, for example, but a lot of them are really just analog chips with a little bit of digital helper circuits, so maybe don't sweat it too much. And if you have to, follow the datasheet recommendations on how to filter the power supplies and all that. Mind the return currents and minimize those loop areas. So that was my hour and 35 minutes. That was pretty good. Another question? Yep.
Do low stuff,
Oh,
how much difference would a low inductance resistor make?
it depends on where it's used in the circuit. I mean, low inductance resistors are usually avoided in output stages because inductance in series with an emitter follower, for example, is a recipe for oscillation or instability. So that's a bit of a different, it's a different problem than signal integrity. Yep.
Is there a way to do some kind of a Faraday concept or to stay?
Oh, can you put a Faraday cage around the circuit and make it better? Well, if you put a Faraday cage around it, you will have good shielding against capacitive coupling. It doesn't really do much against inductive coupling. So I think you're still hooped, at least at low frequency. If you make the Faraday cage out of mu metal, for example, you would get quite a bit of attenuation at low frequency, but it's usually a lot cheaper and a lot better to minimize loop areas and keep things apart. Any other questions related to this topic? Yeah.
Your graphic fairly early on in this presentation where you had two mixed signal devices, left and right.
Mm.
And that was kind of the starting point of how do you manage this thing. What if you took the mixed signal device that you showed on the right and rotated it basically 180 degrees so it was on top? So that way all the digital interconnect strictly on the right side, all the analog.
Yeah, that's basically what I showed in the following slide, except I did it north to south instead of east to west. So unfortunately, that doesn't really solve anything because you still have, I mean, the chips will take up some amount of space. And so you will even if you butt them up right against each other, you will always have that return current that flows across the bridge in one case, but then the coupling between the other, through the other chip in the other case. Does that make sense? Or does that answer? Okay. Oh, could you advance one? I'm still open for more questions, but I just wanted to give credit to the people that I copied figures from and so on, and that was Kuhne with the simulation and also Henry Ott's book. That is a really good read, by the way. So highly recommend it. It is also fantastic against insomnia. Anyone else? We have 20 minutes to go.
So you were mentioning, about the.
Oh, we need a microphone.
You're mentioning about the M clock, and as I recall, that was in the ADC sigma delta parlance, that was modulator clock, and the modulation is the switch cap domain, clock domain, the switch cap network in the front end of the sampler. I do believe that that's the same.
Well, I'll just repeat your question. This was about the M clock and whether that goes into like a switch capacitor, delta sigma, something like that. It's actually in the master clock. So it's just basically a synchronization clock between the receiver and the DAC. I'm not sure how it's used internally in the DAC. That probably depends on the architecture. So, but yeah, but you want that to be fairly clean. So, Sheldon, you had a question?
Yeah, I'm just curious, you're clearly working on a DAC project. Do you see this being released eventually?
Yes.
Okay. But
somewhere between now and the end of time.
All right.
No, I figured that this would not anytime soon, but sometime within the next year, probably. I'll have a DAC. So, yep.
Yeah, apologies if you explain this, but what makes the path in the ground plane underneath the upper conductor, what makes it the path of least inductance at high frequency?
That is because when the current flows, so if you look at, let's say I'm looking at the board edge as a face view, the current flows out in the trace on the top layer, then it drops down to the via or through a via into the ground plane. So the ground plane is solid. And then at RF, it'll follow the trace on trace back. And the reason for that is that if you look at the loop area that's formed by, I mean, into the cross section, there's that band of current or a band of loop area. And the minimum loop area happens to be right as the return current follows the trace. If it were to, let's say, go out the trace and then meander around, then you would have this band of loop area that becomes much, much larger. So basically, the current will minimize the loop area because that minimizes the inductance. And minimizing the inductance minimizes the impedance, and current flows along the path of lowest impedance. Is that cool?
Any more questions?
It's a hard topic to wrap your head around sometimes.
Here, Ben Ma's got a question for you.
Cool.
Yeah, the question is, since RF, you've shown that starts, two kilohertz or so. So that's obviously way down in the audio range. Now, this is more of a audio design question is, why do people not put ground planes in audio boards? Or not saying that all don't, but a lot don't.
Why are people afraid of using ground planes in audio? I think because the idea of the star grounding caught on, and I mean, conceptually, it's much easier to think about the current flows when you have a single wire, because you think that, okay, if current flows nicely in this wire and into this ground plane or into this ground point. The trouble becomes then, where do you put the ground point? A lot of people put it at the power supply, but that means that, say you're building a power amp, you could have this much wire, quite literally, between your feedback resistor and that ground point. And as I showed earlier, I mean, that really wrecks performance. And also, so I think I actually wonder if it was sort of it came out of the electric code. Because with equipment racks and so on, a lot of the time you take the ground from one rack and bring it to a star point and so on. And that works pretty well under those circumstances, but I think applying it in audio is a bit misguided.
Yeah, I mean, it might have to do with.
Hang on, what's that?
The reason why I asked the question is because I don't know any theory, but my brain says that that's what you should do. When I do my board, when I ask about it, I do it because I don't know any of that.
Yeah.
I mean, if I may jump in, that way that way you minimize DC influence, right? If every current consumer returns directly to that start point, you will never have coupling, DC coupling between different elements of your circuit. So I believe that is where it's coming from.
Yeah.
People were afraid of DC coupling. You have large voltages, you have small voltages, large currents, small currents. You're separating all the currents, but only at the DC level, as was shown, right?
Yeah, and I think a lot of people, myself included, assume that audio is basically DC that wiggles a little bit, and that's. I mean, I've done designs at 5 gigahertz, and that's a completely different story. Then the PCB traces don't even connect, and the signal still flows across through capacitive coupling. And that can be pretty exciting for filters and stuff like that. But I think people are forgetting that, I mean, maybe there's a couple of different facets to this where if you're not if you're not developing a very high performance circuit, then you're probably not going to notice the effects of all these coupling mechanisms. If you're living in a world where you don't care about EMC, then you're not going to notice the electromagnetic interference that you're getting. So I think it's in part because people assume that audio is DC, and then they applied the DC rules like you were saying, and then they're neglecting that they also have all sorts of coupling mechanisms, like the mutual inductance between all their grounds. So they end up corrupting their grounds in that case. I hope that's, it was a little bit rambling, but I hope that provides some clarity.
Well, I guess bottom line is that there are advantages of using a ground plane audio.
Oh, absolutely. There's a huge advantage. Especially once you start dealing with mixed signal circuits, but also if you want really low distortion.
I'm just thinking pure audio.
Yeah,
Ju-
or low noise. Yeah.
I just wanted to point out that the early amplifiers that I see very often use the chassis as the ground plane.
Oh,
So you see like just willy-nilly connections, ground connections all over the place.
yeah.
And even if you look at the early Fender guitar amplifiers with a lot of gain, they do the same thing,
Okay.
and it all works out fine.
Yeah.
It's kind of a mystery whether like
Unless you
the
get
early
erosion.
builders knew exactly where to put these
Yeah.
ground points, or whether they.
Maybe they
It
got
really
lucky.
does seem like it's kind of by convenience.
But that would in effect create a ground plane, wouldn't it?
Yeah, the chassis is just a giant
Yeah.
ground plane.
Yeah. Until one of the
So
screws
people
corroded,
used
then
to do it, and it worked fine, and they,
Yeah.
they didn't hum that much.
yeah. Yep.
Hang on, get the mic.
You need to wait for the microphone.
So maybe instead of thinking of audio as being separate from RF and being like DC, we should just think in terms of, 6 dB per decade.
Yeah. That's one way of doing it.
Death is at one end at high frequency, and then we want to be down there.
Yeah.
All right. Does anybody have any more questions? Tom Christiansen.